Recall that congestion collapse occurs when packets consume valuable network resources only to get dropped later at a downstream link. And although the network is forwarding packets, none of them actually reach the destination, and no useful communication occurs, resulting in what we called congestion collapse. We talked about congestion collapse in an earlier lesson in this course. Recall that the goal of TCP is to prevent congestion collapse. In this assignment, you will become familiar with the Mininet environment, creating custom network topologies, running programs in virtual hosts that generate TCP traffic, and learn about TCP, congestion control, and the TCP sawtooth. You'll also see how bandwidth is shared across multiple flows. We are going to explore these concepts in a particular topology that we'll just call a parking lot. So in the assignment, you'll create the topology below with the following parameters. N will be the number of receivers connected via this switch-like topology. The data rate of each link will be 100 megabits per second, and the delay of each link will be 1 millisecond. Now you're going to use iPerf to generate simultaneous TCP flows from each of the senders to the lone receiver. Then you're going to plot the time series of throughput versus time for each of these senders for each of your experiments as you vary the value of n. Your plot should run for 60 seconds. We've given you an initial file called parkinglot.py. Your goal is to fill in the gaps. You'll need to both fill in the part that sets up the topology using a parameter of n, and then you'll need to fill in the part that actually generates the TCP flows between the senders and the receiver using iPerf and monitors the throughput of each of these flows.